Complex numbers can be represented using polar coordinates in a way. Again, recall that a given complex number is represented by a plus bi, and we can rewrite this as an ordered pair, a comma b. Therefore, we can form a right triangle whose base is given by a, whose height is given by b, and whose hypotenuse is given by r. And in this case, this is the modulus of our number. So this is the modulus of a plus bi. Furthermore, we can define the angle between the x-axis and the acute angle of our right triangle to be theta, and we have enough information to rewrite this in polar form. Another equivalence that we have is that our a can be represented as r cosine theta, and our b is r sine theta. And therefore, our complex number a plus b is going to be equal to r cosine theta plus I times r sine theta. And so we define the polar form of our complex numbers as follows. Again, we start with a complex number, and its polar form is of the following form, where again r is the modulus of our complex number, and we also have that tan theta is equal to b divided by a. We call the angle theta the argument of our complex number. Let's look at an example where we compute the polar form given a complex number. This is example number 5. And we want to write 2 square root of 3 minus 2i in polar form, with the restriction that the argument theta has to be between 0 and 2 pi. Let's go ahead and sketch our point. So we'll move over square roots of 2 times 3, 2 times square roots of 3, and then down negative 2. And we can form a right triangle from this. So here's our right triangle. The base is 2 square root of 3, the height is a negative 2, and we want to find the hypotenuse, so this is going to be r in this case, which is the square root of 2 square roots of 3 raised to the second plus a negative 2 raised to the second. Simplifying this, we'll get that this is equal to 4. And in the last part, we want to find what this angle theta is. So let's redraw our triangle real fast. So our hypotenuse is 4, this side is 2, and the base is 2 square roots of 3. And if we divided each side of our triangle by 2, then we don't change the angle at all. But now our base is square root of 3, our hypotenuse is 2, and our opposite side is 1. And so we see that our angle theta here has been preserved, and this is going to be equal to pi divided by 6. So therefore, this reference angle is pi divided by 6, and the angle that we're looking for is going to be equal to a 2 pi minus pi divided by 6. Simplifying this, we'll see that this is going to be equal to 11 pi divided by 6. So if we wanted to rewrite this in polar form, we'd get that 2 square roots of 3 minus 2i is going to be equal to 4 times cosine of 11 pi divided by 6 plus I times sine of 11 pi divided by 6. So now that we introduced the definition of a polar form of a complex number, let's go ahead and look at a very nice property of the polar form. So while we can divide and multiply complex numbers, it's much easier and efficient to first transform our complex numbers into polar form and then use trig. So for example, if we had 2 complex numbers, z1 and z2, and we're trying to multiply these together, let's rewrite them in polar form. So we'll get r1 times cosine of theta 1 plus I sine of theta 1 times r2 times our cosine of theta 2 plus sine of theta 2, where we have an I here. And this is going to be z1 in polar form, and this is the number z2 in polar form. So multiplying these numbers together, we see that this is going to be equivalent to r1 times r2 times our cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. plus I times cosine of theta 1 sine of theta 2 plus sine of theta 1 times cosine of theta 2. And using the sum formula for cosine, we could rewrite this as cosine of theta 1 plus theta 2. And using the sum formula for sine, we can rewrite this entire expression here as sine of theta 1 plus theta 2. Which means this simplifies to be r1 times r2 times cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. So if we wanted to multiply, again, two complex numbers together, it's much easier to transform them first into polar form and then use this formula here. And we have a similar formula for division, which we're going to go ahead and summarize now in the next theorem. So suppose we're given two complex numbers, z1, which is again r1 of cosine theta 1 plus I sine of theta 1, and we have another complex number, z2, which is equal to r2 times cosine theta 2 plus I sine of theta 2. Then z1 times z2 is going to be the equation we just found, and z1 divided by z2 will be equal to the following.